So thank you to the organizers for giving me this opportunity to talk in front of you. I'm going to talk about some work I've been doing with Loga, my advisor. I'm a PhD student at ICTS. And I'm going to tell you guys about radiation reaction and de Sitter spacetime. So what is radiation reaction? Roughly, okay, does this work? Okay, yeah. So if you have some particle which is coupled to some field in whatever spacetime you want to work in, and it's moving in some arbitrary random way, then it radiates. And as it radiates, it loses energy. So one question you can ask is, when it is radiating, so the particle is losing energy, and which means that the radiation as it comes out is kicking back on the particle itself. So you can ask, what is this dissipative force that the radiation that is leaving the particle is putting on the particle itself? Now, naively, you would think, oh, you just calculate the field value at the particle, and that should give you this force. But if you think about it, any charge, if it is moving, say an electric charge, and you ask what is the field at the charge itself, it diverges, right? So you actually have to regulate this problem and really ask what is, after removing the divergent part, what is the dissipative part that is left? And this problem actually has a rich history. People have been trying to figure this out for 100+ years, mostly in flat space. And what I'm trying to do is to ask this question in de Sitter space. So now, this is like the third talk on de Sitter today. So I hope everyone knows what de Sitter is by now. But let me just tell you something relevant to what I'm doing. So de Sitter is really like a very simple type of universe which is expanding. It expands exponentially, and it has a lot of symmetries. And you heard a lot about the de Sitter symmetries before. So, okay, the one way to think about it is it's a dark energy dominated expanding universe, because dark energy does not dilute. It also has a time translation symmetry, which you wouldn't get if you had like a matter dominated universe, because in an expanding universe, the matter would dilute and so change the space time. But dark energy doesn't dilute, which is why it has this time translation symmetry. Another interesting thing is that, say you have some particle sitting in this expanding universe, right? And if there's some particle here, it can send some signal to the particle, to our particle. But as the particle goes farther and farther away, because it's an expanding universe, there will come a point beyond which, if there is anything sending a signal towards the particle, that signal will actually never reach the particle. And so, roughly speaking, this particle has a horizon, and it can't receive signals from things behind the horizon. But Hawking basically taught us that whenever there is such a horizon, the horizon actually radiates at a temperature. And this temperature for de Sitter, for a particle sitting in de Sitter, is basically given by the reciprocal of the horizon. So what is happening is this particle is actually sitting in a nice hot sauna of this Hawking radiation. And we are going to ask what is the radiation reaction on a particle which is sitting in this thermal bath, basically. Okay, so now what does the particle see? The particle sees a kick from its own radiation, which is the radiation reaction which we want to calculate. And it also sees these fluctuations, which come from the fact that you're sitting in a thermal bath. And the nice thing about doing this problem in de Sitter is, because de Sitter has all these symmetries, it's like a very symmetric bath. And so it has a lot of, it puts a lot of constraints on the things that we can calculate. And so it's a very nice open system to study by itself. Okay, so let's ask what are the things that go into calculating this radiation reaction, right? So roughly, you need two things. One is the radiative multiple moment. Okay, we are asking radiation now, so we need to calculate the radiative multiple moments. But the difference between radiative multiple moment and other like static field moments is roughly that if there is a static configuration and you want to find the field, you just need the moments of the distribution, charge distribution. But if you have a radiation problem, you have to take into account the fact that there are time delays because of the things which are spread out, right? So from different points, the field coming to you will come with some different time delays. And so to find the correct radiative multiple moments, what you have to do is also smear you don't just take the charge distribution, you also smear it with some function. In flat space, this function is just Bessel function, Bessel J. And in d sitter, this function becomes a hypergeometric, basically. So you find that and you do the smearing and you get the radiative multiple moment. Now, because we want to ask a radiation reaction problem, we basically want to know how the radiative multiple moment of the particle at one point affects the radiative multiple moment of the particle at some other point. And this is given by some 2-point function. And you can also calculate this 2-point function exactly in d sitter. Okay. So now to understand our results, what we do is once we have these things, we do some approximations and try to see what is happening. So generally what people do, for example, in flat space itself, if you had this problem, you take a particle, it's moving around some trajectory, you take the trajectory to be small, like restricted to a small area. So it doesn't move too much like this. So you take this R compared to the wavelength of the radiation to be small. So you take omega R as small. You also consider the velocity of the particle to be small. And you have already done a multipole expansion here. So roughly speaking, you take the lower order multipoles rather than taking the higher order multipoles first. And these three things together are what is called as a post-Newtonian expansion. In the d sitter problem, what we'll also do is consider this h to go to 0 and then take like finite size corrections. This h going to 0 is roughly like going to flat space limit because you're taking the horizon to go to infinity. And so you'll recover flat space in that limit. Okay, so once you do these approximations, what do you get? So first of all, let's consider just the flat space. Now in flat space, we don't have any h corrections, but we have this flat space post-Newtonian expansion. And what this flat space post-Newtonian expansion together, all these things roughly does is that it allows you to write your radiation reaction force, the force on this particle because of the field. This is, I should have mentioned, this is for the scalar, for a Klein-Gordon scalar. So you have taken a Klein-Gordon scalar field and you're asking what is the force, radiation reaction force on the particle. And it roughly arranges the force in this time derivatives. If you see the first term, the leading term in the PN expansion comes with d time derivatives in d dimensions. Whereas the next term will come with a d+2 time derivatives acting on some combination of 3 x's. And then the term after that will come with some time derivative with d+4 derivatives, time derivatives of some combination of 5 x's. And these combinations can be anything like say del t to the power dxi, del txi, del txj, del txj, and so on. And so you get a lot of terms at each order in PN as you go higher and higher. And some of you may know this is actually just what is the ALD force for electromagnetism, but this is for the scalar thing. So the leading term in the radiation reaction. Okay, so these coefficients, although roughly we get a lot of terms, these coefficients are actually constrained by the fact that the flat space has Lorentz and Poincare symmetries. So these symmetries actually constrain these coefficients that come with these terms. You can't let them be anything. Okay, I'll try to finish. Okay, so what next? Let's ask what happens in d sitter 2. In d sitter 2, you get two very interesting phenomena. One is that this term, if you look at, it gives a d sitter 2 will be like d = 1, And so this gives a del t of x. And roughly this term is like a dm by dt times velocity term. And so it actually causes the particle to lose mass, and the particle follows a rocket equation. Also, in d zeta 2, what happens is that you don't, your 2-point function is no longer local, as in the case of flat space. It also has a tail term, basically. So you have to integrate over the entire trajectory of the particle. Okay. In d plus 1 dimensional d zeta, in a higher order, higher dimensional d zeta, what happens is you have roughly this structure, where this is the flat space thing that we saw, and then you get h square corrections. And now you'll notice that as you go to h square order, the time derivatives decrease just for dimensional reasons. And so roughly what happens is that the structures that you get at h square order is like the structures in 2 dimensions lower. And then h to the power 4 order, you will have structures which are like 4 dimensions lower, and so on. And so the forces are sort of related to, in d dimensions, at its higher orders in h, are related to the forces in lower dimensional d. And so roughly, if you follow this, as you go to high enough order in h, you'll get back the terms that we saw previously, which give the mass loss and tail terms as well. Okay, I have 10 seconds. Fluctuations. I did not say anything about fluctuations, but we can also calculate fluctuations. I won't go into technical details. And just 1 minute. So this expansion is like, in this expansion that we have done, we are looking at 0 temperature plus corrections. And so you get 0-point fluctuations at 0th order. And the finite temperature corrections then, basically, because it's a thermal bath, these corrections come in the correct way so that they satisfy fluctuation dissipation theorem. Finally, I'll just say, we would want to extend this to FLRW, because if we actually want to apply this to, say, a galaxy moving around at large enough scale such that you can actually treat a galaxy to be a point particle, then you would actually want to do it in FLRW, where there's matter and radiation and everything. And this, in that, this H will become time dependent, the temperature will become time dependent. It's a non-equilibrium problem. And so we'll have to work towards getting that before we apply this to real world. That's all. Sorry for being
Thank you, Omkar, for this insightful talk. Are there any questions from audience? Anyone?
So, I mean, can this force be very simply understood as the recoil for the particle? Say it radiates some quantum. Is this the force?
This is more of a classical, like,
yeah, even classically I would expect
yeah. But it is basically recoil, because so it's like a kickback.
Yeah. So, what is the source of the H dependent term, the geometry dependent term?
Okay.
So you said it something.
Here. You mean
yes, yes.
So it comes from 2 places, basically. One is that this 2-point function, which relates the radiative dipole, connects the 2 radiative dipole moments, that also has edge dependence. And this radiative multiple moment, this, like I said, you have to do a smearing. And the smearing function is Bessel for flat space, but you get an edge dependent hypergeometric function when you do the smearing. And these are the 2 things that contribute to the.
And I should be able to recover the flat space result, right, from here?
Yeah. So roughly, if you take the smearing function in d zeta and just take a edge going to 0 limit, you get Bessel. And similarly, you get the 2-point function for flat space individually.
Any other question? Okay, then let's thank Omkar again.